This is a comprehensive guide on the solid software design principles. Solid principles lay the foundation for building resilient and scalable software. Each letter in solid stands for a crucial principle in object-oriented programming: single responsibility, open-close, Liskov substitution, interface segregation, and dependency inversion. We will dive deep into each principle, exploring their definitions, why they're crucial in software development, and how to apply them with real-life examples. To illustrate these principles, we'll use a hypothetical social media application. The first principle is single responsibility principle. The single responsibility principle states that a class should have only one reason to change. That means a class should only have one job or one responsibility. To illustrate this principle, let's look at this code right here. Even though the code is written in Python, these principles apply to any object-oriented language. For example, C#, Java, or Go. I will also mention differences in implementation between Python and other languages when necessary. Here we have a class called Post Manager that's responsible for creating and logging a post. This is a violation of the single responsibility principle because the Post Manager class juggles two tasks of creating and logging the post. And this is problematic for many reasons. The first one is that now the class has multiple reasons to change. If the logic for creating posts changes or the way we log activities evolves, the same class must be modified, which increases the risk of introducing bugs. It is also difficult to scale. As new functionalities like editing or deleting posts are added, the post manager becomes increasingly complex, making it harder to scale and adapt new requirements. Also, it's hard to understand and maintain, because a class with multiple responsibilities is more complex, is harder to understand. New developers or even the original author of the class after some time will find it more difficult to navigate and update the class. Of course, this is a very simple example, but in a big project with complex logic, this becomes a real problem. To avoid these issues and adhere to the single responsibility principle, a better design choice would be to refactor this into a post creator and a post logger class. In the new design, the post creator class is only responsible for creating a post, so it's now easier to scale and expand, and it's easier to change. So if we want to change the way we create posts, we only change this class. The logger doesn't need to change, which means there is less chances of introducing bugs into the logger. And the same can be said about the post logger class. Its focus has a single responsibility, and it doesn't need to change for anything else other than this responsibility. And should we need to change it, the post creator does not need to change. So we have a clear separation on which part of the code is responsible for doing what. As we've seen from this example, this principle aims to separate behaviors so that if bugs arise or changes are needed, they impact minimal parts of the code, which makes the system more robust and maintainable. The open-close principle dictates that software entities like classes, modules, functions, etc. should be open for extension but closed for modification. This means that you should be able to add new functionality without changing existing code. To illustrate this, let's look at this code here. Here we have an analytics class that's responsible for analyzing posts in our social media app. Class analytics has the function analyze that takes a post and a post type. It then branches based on the post type. If it's text, it does text analysis. If it's image, it does image analysis. This is a violation of the open-close principle because the analytics class needs modification every time a new post type is introduced. This way, the analytics class is not open for extension without modification. This is problematic in many ways. Firstly, frequent modifications. Every time a new post type is introduced, the analytics class needs to be modified. Imagine as our social media app grows, we can add video posts, short form posts, etc, etc, etc. Every time we add a new post type, we have to come up here to this if statement and add new logic to it, which means we keep updating existing code for adding new functionality, which risks introducing new bugs to existing functionality. And this makes the system less flexible. This design does not accommodate any future extensions easily, making the system less flexible to adapt new post types or analytics requirements. In my experience, whenever I see a method doing major decisions inside of an if statement or a switch statement, that's usually my cue for refactoring. A method should be focused in scope and should do one thing and should do it well. It shouldn't be making major decisions about the functionality of the app. And we can refactor this to make it adhere to open-close principle by creating subclasses for each post type. Here we have a base post analytics class, then we have a text post analytics subclass, and we have an image analytics subclass. And as you can see here, they both implement the analyze method and they both analyze the post in their own ways. With the new design, we can add new functionality without altering existing code. So for example, if our app introduces video posts, we can just create a video post analytics class without altering any of the existing code. This approach minimizes the risk of introducing any bugs and makes our code more flexible and adaptable for future changes. As we've seen, the open-close principle encourages the use of interfaces and subclasses to allow behaviors to be extended without modifying the source code. As I mentioned earlier, I'm using Python as an example here, but just think of your own programming language and how we would implement this. For example, if you're using C#, you could use interfaces instead of base classes. Liskov Substitution Principle. The Liskov substitution principle states that objects of subclasses should be replaceable with objects of its subclasses without affecting the correctness of the program. In other words, subclasses should extend their base classes without changing their behavior. To illustrate this principle better, let's look at this code here. Here we have a user base class that has a create post method, and all it does is it prints creating post with the content. We then have standard user subclass, and in this case the create post method just calls the create post on the superclass. Then we have an admin user subclass, but this time create post has a slightly different behavior. It first verifies the content of the post. If that verification returns false, it raises an exception. Otherwise, it creates the post. And this clearly violates the Liskov substitution principle, because the admin user class introduces additional behavior in the create post method by verifying the content before creating the post. If the content fails this verification, it raises an exception. If we look at how we use it here, we define publish post method, which is the consumer of the create post method. This publish post method accepts a user variable and a content. Here we instantiated a standard user instance in this standard underscore user object, and we have an admin user object of the admin user class. Now, if we call publish post with the standard user, it works fine, but if we call publish post with the admin user but the post has spam, this raises an exception. This violates LSP because publish post function expects a user type object and calls the create post method on that object. While this works fine for a standard user, with an admin user it leads to a potential value error if this content doesn't pass the verification, which is not expected behavior for a method in the user class hierarchy. Thus, admin user cannot be substituted for user without altering the correctness of the program, and this is how it violates the LSP. Now, to refactor the implementation to make it adhere to LSP, here we have the base user class with the create post method with this common post creation logic. We then have the standard user with the create post method, just calling the method on the superclass. However, the admin user's create post method, it first performs the verification of the content like previously, and if the verification passes, it calls create post on the superclass. Otherwise, it prints post cannot be created and returns false. Now let's look at how we can use this new implementation. Here we have a publish post method that accepts a user base object and the content. It calls the create post method, and the output of that method is a boolean. Here we call it success. If it's success, we print post published successfully. Otherwise, we print post publication failed. We then create a standard user object and create an admin user object and call the publish post with both objects. First, with the standard user we pass hello world. With the admin user we pass this is a spam post. Of course, the output in the first case is post published successfully, and in the second case, post content did not pass verification. Post publication failed. Here, both the standard user and the admin user objects can be used in the publish post function without causing any unexpected behavior or exception. Now, this design adheres to the Liskov substitution principle because subclasses can replace base classes without affecting the correctness of the program. Above, we found the Liskov substitution principle to be the most difficult to explain. So let's use another example that's outside of the social media application. Here we have a superclass shape that has a calculate area method and have a rectangle subclass that inherits the shape class and implements the calculate area method. The rectangle class constructor accepts a width and a height, and its calculate area calculates the area by multiplying the width by the height. And we have a square subclass that its constructor accepts a side argument, and its calculate area just multiplies the side by itself. This example adheres to the Liskov substitution principle because according to the principle, objects of a superclass must be replaceable with objects of its subclasses without affecting the correctness of the program. In this example, square and rectangle are both shapes and they both correctly implement the calculate area method. The interface segregation principle advises that a client should not be forced to depend on interfaces it does not use. To illustrate this, let's look at our example here. Here we have an abstract class user actions that has methods post, comment, and like. We have social media user class that implements it, that defines the behavior for the post method, but for the comment and like, it does not define any behavior. Now this is a violation of the interface segregation principle, because this social media user class is forced to implement those two methods even though it doesn't have to. I want to point out that Python is actually forgiving in this regard, that we can actually delete the comment and like methods here and the code would still compile. Other languages, for example C# wouldn't be so forgiving, and we would have to implement those methods for our code to compile. Now this is really problematic for many reasons. First, it forces unnecessary implementations. As we can see here, the social media user class is forced to implement those two methods that it does not use, which leads to irrelevant code in some classes. Also, this design is inflexible, because any changes to any parts of the system might affect classes that use other parts of the system. So for example here, if the implementation for the like method was changed to use an enum here instead of a boolean, just like what Facebook did when they changed the like into multiple impressions, then the social media user class would have to change as well to adapt that change, even though it does not use the like method. So the change here is inflexible and it causes unnecessary code changes, which might introduce unnecessary bugs. This is also poor abstraction, because this design combines unrelated functionality, which makes it harder for developers to understand and use those interfaces correctly. We have posting, commenting, and liking, which are unrelated functionalities, but they're all lumped together in one interface. I want to point here that when we say interface, we don't mean the interface type that we see in languages like C# and Java. Interface here is a more general term. So the abstract class here is an interface. Now to address this, we can refactor the code like this. We now have three separate abstract classes: postable, commentable, and likable. And the social media user here is choosing to implement postable and commentable, and it provides an implementation for both of those methods. Now if there is any change to the like functionality, like the change we described earlier, the social media user class does not need to change for that, because it only implements what it needs. From all of this, we can see that this principle aims to split large interfaces into smaller and more specific ones, so that clients only need to know about methods that are of interest to them. It promotes more focused and fine-grained interfaces, leading to more organized code structure. I remember I once landed a job because I mentioned in the interview that I prefer single method interfaces. That's how I stood out of the crowd. And that's how important this principle is. The last principle is the dependency inversion principle. The dependency inversion principle states that high-level modules should not depend on low-level modules, but should both depend on abstractions. Additionally, abstractions should not depend on details, but details should depend on abstractions. This is best explained by an example, so let's look at a violating example here. Here we have an email notification service class that has a send email method that's used for sending emails. We also have a notification manager class that depends on the email service. Within its initializer or constructor, it creates a new instance of the email notification service and then uses it in the notify method. Now this is a violation of the dependency inversion principle, because the notification manager here creates its own instance of its dependency, which is the email notification service. Now the notification manager is tightly coupled with email notification manager, which is problematic for many reasons. First, this makes the notification service inflexible. If the system needs to switch to another notification method, the class must be altered. Also, the notification service here is now very difficult to test. Imagine try to unit test this notification service. You won't be able to, because the service creates a real instance of the email notification service. So in a real world example, this would have credentials and secrets and connection strings, things that shouldn't be done in a unit test, because then you would be sending real emails in a unit test. Usually this reason alone forces us to adopt the dependency inversion principle, because you can't unit test with real implementations. Now luckily this is easy to fix. As we can see here from the implementation, now the initializer of the notification manager accepts a service parameter, and it sets its internal service property to the incoming service parameter. It is now up to the caller of the notification manager to instantiate this email notification service and pass it. And this fixes both of our problems. So now, if the notification system is changed from email to something else, The notification manager doesn't need to change. Rather, the caller would create an instance of whatever new notification method we have and pass it here in the notification manager. Then we would call the notify method, which should be available in all interfaces. Also, the notification manager is now unit testable. If we were to unit test this, we would just use a mock notification service here in the initializer, and the mock doesn't need to be a real implementation, it doesn't need to send real emails, and we would be testing the actual functionality of the notification manager. In this tutorial, we looked at the solid design principles, applying them to our social media application. We've seen how adhering to these principles leads to a more maintainable and scalable code base, and how ignoring them can cause significant issues. If you found this tutorial helpful, please like, share, and consider subscribing for more content. Thank you for watching.